Thanks. Yeah, so I'll introduce Gen, a general purpose probabilistic programming system with programmable inference. And this is joint work with Feras Saad, Alex Lev, and Vikash Mansinghka. So first I'll start with some background on probabilistic programming, at least the type of probabilistic programming that we're studying here. And then I'll show some benchmark results using Gen. I'll show a worked example and walk through some Gen code. And I'll discuss some of the technical concepts underlying the system. And then I'll wrap up by discussing some directions for ongoing and future research. So probabilistic modeling and inference is a principled methodology for automated reasoning that is widely used in a variety of fields, including the sciences, robotics, machine learning, and statistics. And in this methodology, a user defines a probabilistic model of some domain, and then they apply an inference algorithm to interpret their data in light of their model. And probabilistic programming systems aim to make this methodology easier to use. And they typically do this by providing modeling languages where the user defines their model, and then by automating aspects of the inference algorithm implementation. So this can provide several types of benefits, including accessibility to a broader audience, more productivity due to faster iteration, and also allowing users to develop more complex models that might be too complex to do by hand. So now I'll briefly discuss existing probabilistic programming systems as well as Gen and how they fit onto these two axes of design space for these systems. So the first axis is modeling language flexibility, and the second axis is inference flexibility. So probably the most widely used and adopted probabilistic programming systems are systems like Bugs and Stan, which use fairly restricted modeling languages. For example, Stan requires that models are differentiable, and it only permits use of continuous random variables, not discrete random variables. Both of these systems provide essentially a black box inference engine, which has a set of generic inference algorithms that are intending to basically fully automate inference. So the ideal case is that a user can just write their model, and then these systems will do inference for them. So another type of probabilistic programming system that was introduced in the past 10 or 20 years have been systems like Eyeball and Church, where they use very flexible modeling languages based on general purpose programming languages. And these flexible modeling languages are flexible enough to handle symbolic reasoning motifs like probabilistic context-free grammars. And like Bugs and Stan, they also use fixed inference engines, essentially a handful of inference algorithms that work asymptotically, so they can give asymptotically accurate results given an infinite amount of computation for any problem you can express in their modeling language. And these systems are designed around this architecture. However, these generic algorithms can't reliably solve all the problems that you can write in these languages because these problems are very heterogeneous. So, anyways. Right, so basically since then, a lot of work has been around extending systems in the style of Church, but providing more affordances for users to customize the inference algorithm and get more efficient and reliable inference. And in particular, a paper that was presented at PLDI last year introduced the Venture system. And Venture introduces a notion of programmable inference, where instead of an inference engine, you're actually providing the user with an inference programming language and the primitives they need to compose their own inference algorithm. And Gen, which is a paper at PLDI, obviously, is based on this new programmable inference paradigm. And Gen builds on some ideas in Venture, but is more flexible in terms of inference programming capability, has a more extensible modeling framework, and is also much more efficient. So in terms of its implementation. So it's much more practical for solving real-world problems. Okay, now I'll just briefly describe some of the benchmarks that we have shown in our PLDI paper to illustrate the types of problems that you can solve with a system like Gen. So first, we consider the task of inferring the 3D articulated body pose of a human from a depth image, a noisy depth image. And we're going to employ a modeling approach called inverse graphics, in which the user provides a parameterized 3D mesh model of an object, like a human, and models the generative process of image formation using a graphics engine. Then the inference algorithm, the inference task, is to go from the observed depth image back to the parameters of this 3D mesh representation. And in our Gen implementation of this benchmark, we use a combination of deep learning and model-based Monte Carlo for inference. So here's an observed image on the top, and in the middle row we have output from a Gen program, which uses a combination of deep learning and Monte Carlo. On the bottom, we have output of a program with output of a Turing, which is another probabilistic programming system. And this Turing system does not support using deep learning for inference in the way that Gen does. And therefore, with the same amount of computation, you get less accurate results. And note that this model is also not expressible in systems like Bugs or Stan, which have more restricted modeling languages. So in a second benchmark, we show that Gen can be used to infer the symbolic structure in a data set. So here on the left, we have a time series data set, and we apply our inference algorithm, and we construct a symbolic expression which contains the semantic structure in the data. So things like the periodicity in the data, as well as the general upward trend. And given the symbolic structure, we can make accurate forecasts forward. And for this problem, we use an MCMC inference algorithm, a custom MCMC inference algorithm. And the only other probabilistic programming system that has flexible enough inference capability to support this is Venture. And the Gen implementation is 100 times faster than the Venture implementation. Okay, now I'll just go through some Gen code and show you a particular worked example. Okay, so here I'm showing 3 synchronized videos. On the left, we see that we see a data stream from a RealSense depth camera, and here lighter pixels represent surfaces that are further away, and red pixels represent missing data. And the goal is to infer the distance from the camera to the floor, as well as the relative orientation of the camera relative to the floor. So to do this, we're going to use a generative modeling approach, and in particular, we can't model everything in the world. Like we can't model the lighting fixture on the ceiling or all these chairs. So for this task, it suffices just to model the floor and the ceiling. So in the middle, I'll start it again. In the middle, we are showing the synthetic depth rendering of the virtual floor and the virtual ceiling. And on the right, we're showing in blue the pixels that we think belong to the floor and the ceiling as a result of our inference. All right, so here's the Gen code for this demo. Gen code basically has 2 components. There's a model, which is a generative model, written in one of Gen's modeling languages, and then there's an inference program on the right. So generative models are essentially simulators for virtual worlds and virtual data based in those worlds. You can think of, and this particular model is implemented in Gen's dynamic modeling language, which is embedded in Julia. The inference program is a regular Julia program that takes as input some real data and then tries to generate virtual worlds that explain that real data and are also plausible according to the generative model. All right, so now I'll walk through the generative model in a little more detail. So it's a lot like a regular Julia function. The first thing it does is it decides, okay, there's some floor in the world, a floor plane. Then it samples a random variable, which is going to be the height of the camera off of the ground. And it says there's a uniform distribution on that between 0.2 and 2 meters. Then it uses this trace language construct in Gen to say that I want to record this random variable in the execution trace of this function that I'm running. And I give it a unique name. In this case, the name is Z. So here we sample a value of 0.7 meters, and we add it to the trace. And as we'll see later, execution traces of generative function are the key data abstraction in Gen. So next we sample the pitch angle. So a pitch of 0 corresponds to facing up, pitch of pi/2 is facing forward. And we also sample a roll angle, which rotates the camera around its heading vector. And finally, we render the synthetic depth image. So this is what we would expect to see with these pose parameters, Z, pitch, and roll. We'd expect to see a plane sort of going off into infinity. Then we have a noise model. So we add some noise to the image, and this represents our observed image. So that was the generative model. The inference program starts off by obtaining a piece of data, a frame from the depth camera, so that's showing in the upper right. Then the first thing it does is it obtains an initial execution trace of the generative model. And it asks Gen to generate an execution trace where the observation random variable is bound to the actual data it got from the depth camera. However, all the other random variables are sampled from some prior distribution, basically, so they are the incorrect values. So the purpose of this for loop here is basically to iteratively refine those values and make them better explain the data. And this is an MCMC for loop, if you know about MCMC. So here is a video that's going to repeat a couple times showing the iterative process of convergence there. So we start off with some strange hypothesis, and then we gradually tweak these variables to better explain the data. Basically, we're fitting the floor to the image. So at the end of this program, we get a final execution trace, which, like I said, contains the correct values for pitch, roll, and z. Now, what is happening inside this inference program? So each of these statements here is taking a trace of the model and returning a new trace of the model. So we're iteratively updating this trace with this gen.mh operator. And mh stands for Metropolis Hastings. And here there's two types of Metropolis Hastings operators that gen is letting us use. The first one on this line takes a selection of several random variables and proposes new values for all of them at once. The other three lines here focus on a single random variable at a time and try to adjust them by making small local random walk moves. Okay, so that's the inference program. So now Gen should let us ideally iteratively adjust the model and the inference program pretty efficiently. So say we wanted to model the ceiling too, right? So modeling the ceiling would be important, for example, if we're facing up, because then the floor is no longer in our field of view. So to model the ceiling, well, we need to know how tall the room is. So unless we know that a priori, we have to make that a random variable too. So we just add that to our model. We say that there's a prior distribution between 2.5 and 3 meters on the room height. Now that we added a new random variable to our model, we also need to augment our inference program. So here we're going to say that we also want to add the room height to the global move we're making at each iteration. And we also want to add a local move specifically for the room height. And now when we look at our inference algorithm convergence, we see that both the floor and the ceiling in the virtual world, but it's pretty much the same as before. Okay, so one of the core contributions of the system is the inference programming capability and its abstractions. So these abstractions make it easy to iteratively experiment with different inference algorithms. So I'll show some examples here. So in our original inference program, we had just a single static image that we were doing inference over. Suppose we wanted to do inference instead on a stream of these depth images, like we saw in the original video. So to do this, we can just change our for loop into a while loop, and then we can obtain a new frame from the depth camera at each iteration, and then we can use Gen's update operator to replace the previous frame with a new frame in the execution trace. And when we do this, we now get a tracking algorithm, which is basically tracking the pose of the camera from a video stream. And if we plot out several runs of the inference program and its behavior over time, we see that most executions of this program will converge to the right answer in around 50 frames, and we see the expected oscillation for the roll angle. So one question is, how sensitive is this inference algorithm? Sorry, how sensitive are these results to the details of the inference algorithm? Like, why do we need inference programming languages? Why can't we just have inference engines, for example? And the idea is that while making the performance is sensitive to small changes. So say we comment out one of these lines, we no longer have these global moves. So the new results without the global moves are shown on the right, and here it takes about twice as long to converge typically, and some traces never really converge to the right answer. If we instead comment out these other types of moves, these local moves, now we get answers that are wrong but in a different way. So the take-home message here is that users need flexibility of programmable inference in order to devise effective and reliable inference algorithms for applications, and that Gen's high-level inference abstractions make it possible to specify effective and reliable inference algorithms in like tens or hundreds of lines of code at most. Okay, so I'll briefly go over some of the technical concepts now underlying the system. So, like I said, one of the key ideas is to separate the modeling language implementation from inference algorithm specification. So, because in Gen, inference algorithm specification is a user task, and we don't want users to have to think about modeling language implementations. And this is a key difference from many other probabilistic programming systems where if you want to add a new inference algorithm, you basically have to extend the compiler for the modeling language by introducing new behaviors for example, sample statements. And the way that Gen achieves this separation is by introducing a black box interface for modeling components called the generative function interface. And I'm not going to go into details, but there's just a set of operations here dealing with generative functions and their execution traces. And having this separation allows us to actually have multiple interoperable modeling languages because it's a black box interface that's language independent. So for example, we have some languages that are more expressive and less performant, like the dynamic modeling language. We also have languages that take the other trade-off, the static modeling language, which supports incremental computation, but it's a little more restricted. We also have, because this is an extensible system, we can incorporate TensorFlow code by writing a little embedded TensorFlow language for pure functional TensorFlow computations. And then we have a combinator language which allows us to express common patterns of repeated computation, like mapping or unfolding. And then also we provide the user has the ability to implement their own generative functions, and this is really important for incremental performance optimization for real-world problems. And on top of that interface, there's an inference programming library, which supports a large number of inference algorithms. And in particular, Gen is focused on Monte Carlo and variational inference algorithms. So one of the key dimensions of inference flexibility that Gen provides is the ability to use domain knowledge to make the inference algorithm more efficient. So for our working example I was talking about earlier, we know that if we can find 3 points in this image, 3 pixels, that are all on the floor, then we can just immediately fit a plane to those 3 points. And then we can analytically solve for our pose relative to the plane. Right? So that's a pretty easy problem. Why do we need all this elaborate inference machinery? Well, we would need to do that reliably because there's noise in the image and because there's other objects in the image, like not all pixels are on the floor, right? We might need to pick 3 points, pick a large number of those triplets, basically. So you can imagine building some sort of heuristic estimator for your angle based on that idea. And Gen lets you incorporate that sort of idea into your inference algorithm and maintain your asymptotic consistency guarantees. So on the right here, I'm showing a video, the data is changing over time. On the left, I'm showing what you would get if you used a generic proposal distribution, which is what a lot of probabilistic programming systems restrict you to using. In the middle, I'm showing what a data-driven proposal distribution is giving you, and you can see that it's adapting to the image, and in particular, it's placing a little more probability mass near the correct answer. And, right, so now both generic and data-driven proposals can give you asymptotically correct answers with enough computation, but data-driven proposals sort of start you off at a more accurate starting point. So here we're basically saying if you know more knowledge, if you have more knowledge about the problem, Gen can let you leverage that knowledge to get better performance. All right, so I'll briefly talk about a couple of research directions. So first, because Gen has an extensible set of modeling languages, we can always add more, and these languages can exploit special structure in the modeling language. In particular, you can have specialized compilers, which use specialized algorithms. I think a very exciting area is around inference programming languages. So here, Gen's inference programming language is basically Julia, but you can imagine having specialized languages for inference programming that support operations like static compilation, verification of inference, as well as synthesis of inference programs. And finally, we're interested in building higher level domain-specific languages on top of Gen, and in particular, we're working on data table cleaning language, as well as languages for computer vision. And these systems can provide higher level functionality as opposed to Gen's relatively low level inference programming support. Okay, that's it.
Results about like if I stick to a certain fragment of the inference language that I know I'll still like have the right asymptotic properties, right? Or can I just write down an inference procedure that would be garbage?
Yeah, so you can write down garbage inference procedures. Part of that is, yeah, you're right. Basically, if you restrict yourself to some subset, then you can get asymptotically correct results. For example, if you just use for loops with MH operators, and you sufficiently cover enough of the random variables, then you get a converged algorithm, right? So we're not currently verifying that you do that, because it's just general Julia code. But that's like a super interesting area of work, and we are working a little bit on that, actually. But yeah, and one of the reasons why we wanted to allow users to leave the asymptotic regime is because we want the tool to apply to cases where maybe asymptotic convergence isn't the main point, like maybe computer vision, things like that.
So you mentioned that you have a TensorFlow sublanguage. Can you compare the expressiveness of that to Edward?
Right. Yeah. So I think the main difference between Edward and there's many differences, but one of the key ones is around so one is flexibility of the modeling language, basically. So we can use arbitrary Julia code that then invokes these TensorFlow computations. That's a very different programming model than Edward's. And I think the more important difference maybe is around inference programming. So the whole style of inference programming is very different. So here we're focused a lot on Monte Carlo inference, things like very customizable MCMC, whereas Edward is more focused specifically on deep variational type approaches.
I had a quick question on so the inference procedure you showed, this is for something based like MCMC type something, right? So how would this look for customized variational inference?
Yeah, so for customizable variational, there's two pieces, right? One is you write your variational approximation family. So that's like one piece of a variational algorithm is what is these class of distributions that you're training, right? And that actually is represented also as a generative function. So we use the same representation for generative models as we use for variational approximating families. The other type of customization you might want to do is actually customizing the optimization algorithm, right? And since Gen is a Julia inference programming library, essentially, that would just be like some Julia code using our generative function interface to do the parameter updates and things like that. But you could write your own optimization algorithm in Julia, essentially. Yeah.
All right. Thank you.
Thank you.